And here we go. Okay, thank you very much. Please go ahead, Gustavo.
Okay, sure. Can you see my slides? I assume you can.
Perfect.
All right. Okay, excellent. So thanks a lot for the invitation. Thanks a lot for the opportunity to be here. Let me give you a little bit of my background, right? I mean, so that you understand where I come from and why am I saying the things that I'm saying. And also give you a little bit of a background for this presentation, right? So I'm a professor of computer science at ETH. I used to work traditionally in databases, data processing, large-scale data processing, distributed systems, and so forth. And over the last 10, 15 years, I have moved more and more towards hardware specialization, hardware architecture, but with an emphasis on data processing. And of course, this is something that is very relevant in the context, for instance, of cloud computing on data centers. I'll explain you why data centers are moving in this direction. And it turns out that a lot of these ideas also resonate quite a bit for people who are working on computational science of different types, because at the end of the day, what we're all doing is struggling with growing amounts of data that need to be processed. Everybody has a bit different requirements. In your case, high energy physics, right? I mean, I'm also relatively familiar with what is happening in CERN, right? Through my interaction with people in physics here at ETH and with Anna and so forth, right? You have a very strong latency requirement, and you actually have to operate very close to the sensors to actually do very heavy data reduction. In other areas, they have slightly different problems, but I want to sort of make you aware that some of these problems are actually common across different areas, and I want to discuss some of the trends that are happening around that. About the topics of the talk, this is based on a talk that I gave at CERN a couple of months ago at a school that was being organized, and the topic seemed to resonate with quite a few people, and then I was invited to give the talk again. I'm very happy to do that. It is something, the first part, it is something that even people in computer science typically are not entirely aware of what are the trends that we are having in industry. So I will actually discuss those trends, and I will be very happy if you disagree. If you have questions, feel free to interrupt me. I think I see everybody who's there, right? I mean, so if you have questions, just raise your hand or just simply turn on your microphone and interrupt me, because if I'm not looking necessarily at the screen at that moment, I might not see that you have questions. But I'm happy if you interrupt in the middle of the talk, right? I mean, feel free to do that. Okay. So with that, let me start with the talk, and let me start by pointing out that we are in the hardware era, and this is something that a lot of people are probably aware, but there is a little bit less awareness that this has been going on for quite some time. So there is a very interesting book, especially for those of you interested a bit on the history of how technology evolves. This is a book from 2011. It's a report from the National Research Council in the United States. And at the time, they were worried about the impact of multicore. And just to cut a long story short, what they were saying is that, well, now computers are multicore. The problem is that we really don't have a good hold on how to program parallel computers. And multicore really does not buy you a lot of additional performance unless you can actually exploit parallelism, and there are limitations to how much you can exploit parallelism at any given application. This is a situation that they thought it was not going to change in the future. Now that we are in 2024, right? I mean, now quite a few years later, we can confirm that in fact the situation has not changed. And at the time, they were saying the alternative is specialization. So we are going to go away from general purpose CPUs, and we are going to move more and more towards specialized hardware in order to solve the problems that we are having in terms of dealing with larger workloads, larger amounts of data, higher demands in terms of latency and throughput, and all those sort of things, right? And the interesting thing is that as they point out, and again, I'm presenting this in a very summarized way, but I think the message really reflects what is the spirit of what they're saying, is that unless somebody comes up with a great new invention on how to do processors, how to do CPUs, somebody comes up with a new way of doing electronic circuits, right? I mean, or we have a problem because the situation is going to continue for the next 20, 30 years. So this is 2011, and by the way, this report is available online, or used to be available online. So if you look for it, probably you will figure out how to actually download it. Now, as I said, this is not a new concept. For those of you who are familiar with the ACM, right, which is the Association for Computing Machinery, right? I mean, publishes a lot of journals and runs a lot of conferences in computer science. They have a magazine called Communications of the ACM that they publish generalist articles, right, I mean, about computer science. And there was this very interesting one published a couple of years ago that it was entitled "The Decline of Computers as a General Purpose Technology." The point that they were making is very similar to the previous report that I discussed, but they were actually making more of an economic argument. They were actually pointing out, and this is the graph that you see on the left, the blue one, that the performance improvement on microprocessors over different generations has been going down. This is kind of a funny graph because, of course, you realize that the periods of time that they have in there do not match, right? 94 to 2003, 2011, 2011, 2018, and 2015, 2018. The period gets smaller and smaller, so of course the gain is going to become smaller, right, during that period. But in general, this is actually true. The performance that we are getting out of new generation of microprocessors, right, is actually going down. This is one of the reasons why people use multi-core, right, because cores are not getting any faster. So the solution is actually put more cores and then hope that people know what to do with it. But even more relevant, perhaps, is what you see on the graph in red to the right, is that the microprocessor performance per dollar improvement, right? This is what is going down. And I'm sure many of you will have heard this. Creating the fabs that actually do the microprocessor cost a lot of money. If you want to improve the performance, you need to actually have smaller size features, right? I mean, a smaller feature size on your microprocessors. This requires new technology, requires new fabrication methods. This cost on the order of billions. And the problem is that if the performance gain is not significant enough, then the motivation to switch to this new technology is not there, which means that the return on investment on buying one of these new fabs is going to take longer to be recovered if you are ever going to recover it, right? I mean, so that actually slows down the improvement in processors. And this is without getting into the discussion that, of course, we can also have about Moore's law and linear scaling and many other things, right? So in essence, the message of this paper is that technology is slowing down, and because it's slowing down, there is less money to advance the technology. Because there is less money, technology is slowing down, and this is a bit of a self-fulfilling prophecy, right? That we are really not going to have computers as general purpose technology. And like the report before, what they say is that what is going to happen is that we are going to have high degrees of specialization. Now, for most of us, and most of us includes people in computer science, this specialization is actually difficult to see. I mean, of course, everybody sees that we are moving more and more towards GPUs, away from CPUs, because of AI and LLMs and all those sort of things. But at the end of the day, we're all confronted with a screen and a computer and an operating system that looks very much the same thing that we have had for the last decades, right? So what is actually driving a specialization at a very large scale and very, very quickly is the cloud. The cloud is really a big game changer because it represents a new business model for the IT world. Instead of being a manufacturing system where you produce hardware and software and sell hardware and software, it changes to a service model. It has economies of scale that we have never seen before, not even in supercomputing centers of HPC centers, right? I mean, so has been rarely that we have had data centers that has millions and millions, and we don't only have one such data center, we have potentially hundreds of those data centers that are at a scale, as I said, that we have never seen before. And these data centers also support very large, very heterogeneous, but very large workloads. As a result of this, what in the IT world, we used to have this killer app thing, right? I mean, if you were presenting an idea, people would say, okay, what is the killer app, right? I mean, what is the thing that you're going to be able to do that cannot be done today, or that is going to be fundamentally different from what has been done before? The issue is that while in the past, if you wanted to have a product or you wanted to have a company that produces some software, you really needed to have a killer app. Today, the cloud itself is its own killer app. If you can actually come up with a hardware or software solution in the cloud that provides an improvement of 1 or 2%, you are in business, because at that economies of scale, if you can save 1% of computation, or you can save 1% of the cost, knowing that one of those data centers cost a couple of billion, right? you're actually talking about a very serious amount of money. And that actually changes the equation in a very fundamental way. The other thing that is happening, which is also something that many of my colleagues in computer science, and I know this from experience because I have given this type of talk a few times, not only here at ETH, but also at other universities, right? And this comes sometimes a bit of as a surprise, is that the cloud providers, the hyperscalers, right? The Amazon, Microsoft, Google, Facebook, Alibaba, Tencent, and so forth of this world, actually dominate the market. By now they buy 70, 80% of all the components that we have for computing, CPUs, memory, disks, networking, cables, and all those sort of things. Which means that they really dominate the market. Today, it's very difficult to come up with a product, a new CPU, or a new form of memory, or something like this, if the hyperscalers say, we don't want this, because that means that upfront 80% of the market does not exist. And then you're going to have a very hard time paying for the advances in technology that you need to produce this new CPU when the providers tell you, the hyperscalers tell you, we're not going to use it. At the same time, of course, because of economies of scale, these cloud providers can actually go to the hardware vendors and tell them, look, I'm interested in this type of CPU, but you actually need to put these features in there. And this is what is actually happening. We're starting to see more and more features that appear on CPUs, on the architecture of computing, and on configurations of computing that are really nothing that is truly relevant to any of us as normal users, but are very, very, very important for the cloud. Right? And this is actually something that is driving this specialization. Right? The fact that a company like Google or Microsoft can actually go to Intel and say, look, I'm going to buy your next CPU, but you need to put these instructions, and these instructions are there just to support my particular way in which I run my workloads in the cloud. And this is a situation that is very, very new. The other thing that is happening in the cloud, right, is that the level of investments that we are having in the cloud are actually huge, right? So these are two articles that I put here as a reference, right? I mean, they are from Deregistered, right? I mean, there is this online magazine that talks about IT and so forth, where they talk about what is the yearly budget now for Microsoft and for Google, driven by LLMs and AI. And what is interesting is that the budget for one is 48 billion with B dollars, and for the other one is $50 billion. And most of that budget is going in equipment, is going buying hardware to run LLMs. So once you are spending money at that level, once your expenses are that high, there is a point in which you really, really want to make sure that the hardware that you're buying or the hardware that you're deploying, right, it really solves your problem. And this is what is actually driving specialization. Everybody here, I assume, has heard about Google TPUs, right? I mean, that's a very good example of a specialization. TPUs appeared at the time that people were doing neural networks before transformers, but it really doesn't matter. The people in Google realize for supporting neural networks, one of the things that we need to do is actually have very, very efficient matrix multiplication. And this is what the TPU is. The TPU is an integer matrix multiplier that is far more efficient because it only does integer matrix multiplication, right? I mean, for particular integer sizes. And this is far more efficient than using general purpose GPUs, and of course, much more efficient than using general purpose CPUs. This is just one example, but I want to sort of give you a couple of additional examples, right, of what is happening in these data centers, right? So what you see on these two graphs, this is a little bit more coming from papers, right? I mean, that talk about behavior in the cloud. The one on the left, it is talking, it was published last year at SOSP, it's an operating systems conference, right? Systems conference. And this one was a surprise to me and to many people, right? Even people aware of what's happening on the cloud. Because what the graph shows is the number of remote procedure calls that are made on particular type of distributed architectures in the cloud. And what I want to call your attention is to the exponents that you have. It's 10 to the 5. This is 100,000 remote procedure calls. The degree of distribution and the size of these systems, again, is something that we have never seen before. If you will have asked me a couple of decades ago, right? I mean, what I thought about building a distributed system where an application will actually make 100,000 remote procedure calls, I will tell you, you're crazy. This is just simply not going to happen. Today, we have them. And of course, 100,000 is the limit that you see in there, is the upper limit. But you see that it's very, very normal that a procedure or a method, right, or a service will actually make between 100 and 1,000 or potentially several thousand remote procedure calls. This is a huge overhead. And this huge overhead is known. The graph that you see on the right, this is actually taken from ISCA, it's a computer architecture conference published in 2015. But the situation has not really changed since then. This is a paper from Google, if I recall correctly, and they are talking about something that is called the data center tax. What is the data center tax? The data center tax is the number of CPU cycles that are going into simply running the infrastructure, not actually running the applications, by running the infrastructure. And you see that if you take compression, you take allocation, hashing, protobufs, that is for remote procedure call, the overhead of remote procedure calls, memory movements that you need to have in the cloud, right? You're actually spending more than 25% of your CPU cycles, right, on simply running the infrastructure. You're not running any application. Now, of course, if you are a cloud provider, you make money by renting the compute infrastructure, and it turns out that a fourth of that infrastructure, right, you're using it for running the cloud, right? So that's a kind of like very inefficient way of doing things. So these two papers are actually very interested if you want to see where the cloud is going, especially the 2015 is particularly interesting because they almost predict, although at the time they're not making predictions, but they are saying what needs to happen in computer architecture, right, to better support cloud workloads. And a lot of the things that are happening now in processors and in architectures and configurations, right, I mean, actually reflect a lot of the ideas that they have on that paper in terms of where do you want to minimize overhead, what type of instructions you want to have, what type of behavior you want to have on the CPU and things like this. Again, taking into account that the workloads that they have in the cloud are not the workloads that normal people like us typically run. The other thing that is happening, of course, is that there are things in that graph like compression. Why are you spending almost 5% of your CPU cycles in compression? Because in the cloud, everything that goes to storage has to be compressed, and when it comes back from storage, it has to be decompressed because the cloud has disaggregated storage, right? You also today, probably you will add encryption to this thing because now on the cloud, everything has to be encrypted and decrypted and things like this. So that probably will add to this overhead. And then because of the way the cloud works, right? I mean, the memory allocation, loading your virtual machine, right? The image for your virtual machine, loading your data, loading your application, then starting and things like this actually takes quite a bit of time. So the result is that we are starting to see, and we have actually been seeing this for the last years, a lot of very specialized architecture and hardware support for this data center tax, right? So what you see here is an ASIC developed by Microsoft, and this is just for compression. Why? Let me just go back. Look at that graph on the right. Compression is 5% of the CPU cycles. You don't want to burn 5% of the CPU cycles that you have on your machine, right? That you can actually rent to people and actually make money with it. You don't want to burn them on compression. So what you do is you put on your machine an ASIC that actually does compression. Microsoft came up with Zipline. There is a number of algorithms for doing these things, and Corsica, which is actually the ASIC, the hardware that will actually do this. And that way the compression is not done by the CPU, but is done by an accelerator. This is just one example. There are many, many such examples. Let me just actually mention a few more. Microsoft has now something called Azure Boost. In the past, this used to be called Catapult. This is a small, if you want to call it motherboard or a small computer that lives inside a computer, right, in the cloud. And what this Azure Boost does, it actually manages the virtual machines, actually takes care of a lot of the security, a lot of the booting and controlling and monitoring. But it also, what it does, it actually manages networking and manages storage and things like compression and encryption and all those sort of things. Why? Because in the cloud, you need to provide virtualized networking. Virtualized networking is very, very expensive with the CPU, right? I mean, there are papers from Microsoft where they say that at the scale that they operate, network virtualization, network function virtualization can take up to like 6 to 8 cores in a machine. And again, these are cores that are not used for anything else. So they actually have a full accelerator that actually takes care of network virtualization. That way you are not actually using the CPU. And again, all these things are not things that are available to people. These are just things that they deployed internal to the data center. as additional accelerators, if let me just skip this in the interest of time, there had been many. Some of them are successful and are deployed and are being used. Others have been an attempt to sort of see what happens. For instance, Aqua. This was a caching layer implemented at Amazon. This caching layer was actually used for Redshift. Redshift is the large-scale data analytics platform of Amazon. And what Aqua was doing is introducing a caching layer with SSDs between S3, that is the storage level, the object storage of Amazon, which is based on hard disk drives for cost reasons, therefore it's slow. And then the caching layer is implemented with SSD. So if you are actually going over the data several times, then it's cached on the SSDs, and next time you will actually be able to access it faster. But what is interesting is that on that caching layer, there is an FPGA, and that FPGA, what it does is actually early filtering of the data. You can actually push down operations like a string comparison, a string-based filtering. You can actually do selections, you can do projections, a number of database operations that actually do data reduction before the data is moved to the computational nodes. It's just another form of data reduction that is a very common theme that is appearing in the cloud. And you see, people are actually resorting to very specialized architectures for doing this. Right? And of course, if we go to ML and AI and all those sort of things, and this is a topic that will take me a long time. I don't want to go into that, right? I mean, but of course, the figure that I have on the left, this is the TPU, right? Version 2, version 3. By now, I think they're on version 5, right? So this has been evolving a lot in Google. But you also see that all the hyperscalers are actually coming out with their own version of GPUs. What you have on the right is this Maya 100, right? I mean, from Microsoft, right? I mean, that, like the TPU, is actually intended to come up with hardware that is far more specific, far more specialized to the particular workloads that Microsoft is running. In this case, probably AI and ChatGPT and things like this, right? As opposed to using general purpose computing in the form of a CPU or a GPU, which are first far more expensive, but also not as efficient as this type of highly specialized devices. Okay, so this is a little bit about the background and where we are, and just to sort of convince you of where things are going and why things are going in that particular way. Let me just make a small break here. And if anybody has questions or comments or disagrees with what I said, I'll be very happy to hear it. And otherwise, I will continue. So anybody has any questions or comments? Right, I don't see any hand. I don't see anybody saying anything. All right, so then I will continue. So what can we do with new hardware? And that's something that we have been exploring in our group, but of course we are not the only ones. There are quite a few people doing this type of work, right? And these are the type of things that I think will also be relevant to you, because to a certain extent, what you're doing, especially for the new versions of the detectors, right? I mean, that you're coming up with CERN, you're actually trying to do very similar things, right? I mean, even if it is at different scales, different cost point, different applications, right? But conceptually, you're trying to do the same thing. So first, let me actually do a little bit of marketing, and this is something that Anna is aware of it, but something that can be interesting to some of you. At ETH, we are running what is called the HAC cluster, right? I mean, the heterogeneous accelerated compute cluster. This is something that we're doing together with AMD, which has a number of these clusters all over the world. There are 2 in the United States. There are 2 actually in Europe. There is the one at ETH. There is the one in Paderborn, right? I mean, that is more for supercomputing. There is another one in Singapore, and there is a very recent one that has opened in India. And this is supposed to be a public cluster for people doing research. Eventually, I will send you the slides, and of course, you have the recording, so you can actually go and find the links there. But otherwise, if you just go do a search for ETH Zurich HACC, you will actually find it, right? And what we have in there is rather diverse and heterogeneous architecture that has been evolving over time. We have now 3 different types of clusters. We have a cluster with Alveo cards, is the one that you see on the left, that has U250s and U280s, right? I mean, these are different Alveo cards, FPGAs, on relatively large servers. We have each server has around 4 FPGAs. They are virtualized. You can actually, once you get access to the cluster, right? I mean, you can actually reserve one of those virtual machines and then do your own your research on those FPGAs. We have another rack that actually has 10 U55Cs, which is a newer version of the Alveo cards. And we actually use these for distributed experiments. They're connected through a 100G network. And that's what we do to actually do, for instance, distributed machine learning. And whenever we are trying to do large scale data processing, or we have a lot of data, we don't do it with one single FPGA. We're doing it with 10 of these FPGAs, right? And the last machines that we have are very large machines, so that you also get a bit of an idea of the extremes that are starting to appear in the market, right? I mean, where we have two multi-core CPUs, the EPIC, right? These are some of the largest that AMD had, especially, you know, when we got these machines, they were definitely the largest. There are 4 GPUs, the MI200, which is a very, very large GPU with quite a bit of memory. And there are 4 FPGAs as well in there, right? I mean, and everything is connected to a 100 gigabit switch. And you can actually imagine a lot of very interesting applications, right? And I'll give you a few ideas of what we're doing with these things on these machines, right? So if you're interested in using this cluster, this can be actually accessed to the AMD University program, which you can actually find online. Otherwise, contact me, and actually I can actually help you to gain access to this if you are interested in having access to this infrastructure for research purposes. All right, so what have we been doing with this thing, and how are we trying to sort of improve efficiency of things? Well, one of the first things that we have been doing is actually build network infrastructure that allows us to sort of move data between storage and compute nodes in a more sensible manner, right? I mean, so we have 2 systems. One is EasyNet. EasyNet is a 100G TCP/IP stack for FPGAs. This is actually open source. It's actually written in HLS, in high-level synthesis, right? So it's actually something that can be modified. You can actually go and play with it and put the things that you want to have in there and so forth. We also have ACOL. I'll talk about it a bit later. What ACOL is a collective communication library that we have developed together with AMD that allows you to do a scatter gather and broadcast and all those sort of things. For those of you familiar with high-performance computing, you will know this from MPI and OpenMP and those type of things, right? So this is one of the things that we have been doing, and the one that is actually more interest now, not only in the data center, but we're also getting a lot of requests from high-performance computing is RDMA, right? I mean, remote direct memory access, because if you're actually moving large amounts of data, having the ability of putting the data directly into the memory of the compute or reading directly from the memory without involving the CPU is a very interesting thing. So we have our own implementation of RDMA. The numbers that I have here is for an older implementation, right? I mean, that we published a couple of years ago. We have a new implementation called Balboa that we are at the moment writing a paper and doing the last touches to the implementation. That is also open source. It's available. And what is the interesting thing? I'm not going to get into the performance details, right? I mean, but what is interesting is that if we compare with the performance that you get by using a Mellanox card, right? I mean, at 100G, we're actually getting very similar performance. And what is interesting is that because we are implementing this on an FPGA, we can actually put computation on the FPGA that will actually work at line rate on that data that is coming from RDMA. And we have quite a bunch of ideas that we have done from data structure traversals, right? I mean, on remote machines. So for instance, if you have data that is sitting behind an index, the problem with using this data remotely is that you need to sort of go and get the first node, bring the first node, you traverse it, then you go again. So there's many messages going back and forth. By having this implemented on FPGA, what you can do is you can actually implement the data structure traversal on the remote machine. And that way you're actually minimizing the number of round trips that you need to do. And this is actually something that is very useful whenever you're doing large scale data processing, but also in high performance computing and so forth. But in general, the ability to actually do RDMA across machines actually immediately enables quite a few interesting things, right? The other thing that we have been doing is that because the commercial shells that you have both in AMD FPGAs, but also the ones of Intel, right? I mean, soon to become Altera, if it has not become Altera already, are not really geared for doing data center type of developments, right? And that's kind of a separate discussion why this is the case. So one of the things that we have done that has proven to have quite a bit of acceptance, right? I mean, in many areas, is we have built our own shell. It's called Coyote, again, open source, and now we're in the process of coming up with the second version of Coyote, right? I mean, adapted to the new boards that AMD has. And we are working together with AMD on this because the idea is to actually make Coyote the open source shells for these FPGAs. What Coyote buys you is that we have, for instance, separate reconfigurable regions. So you can put up to 10, but of course, if you put 10, they are all very small. But typically, you can put between 3 and 6 and get very, very reasonable regions. What is the advantage of having these regions is that you have the equivalent of having multi-core. We can actually put different logic that is processing data, doing different things potentially for different users, or multi-threads for a different user, and so forth, right? These virtual FPGAs, as we call them, right, are actually isolated from each other. They have unified memory access to the memory of the host, so they actually also pass pointers back and forth with the CPU. And they have access to the network using a very simple interface. So whenever you develop your logic, you do not need to develop the networking with itself because Coyote, the shell, has a network, right? The idea with Coyote is to actually make the FPGA look like a normal computer. Whenever you start the computer, the network is already there, and the access to memory is already there, and the interface is already there, and you don't have to build that yourself every time, right? And there we have TCP/IP and RDMA. These are the systems that I have just mentioned, and we have been building on top of them over time, right? Now, the latest thing that we are doing, and this is also a little bit of marketing, but of course, if anybody's interested, we are happy to have more people joining the effort, is we have a project called Slash, and this is together with AMD Research in Dublin. And what we're doing is we're actually building the equivalent of a smart hub. The idea is that because we are moving into more and more heterogeneous computing, where we have GPUs, DPUs, CPUs, memory storage, smart storage, persistent memory, you name it, we want to actually build through an FPGA, we want to actually build an interface where we can actually put the control plane that will actually act as the traffic controller, if you wish, for all these devices. So traffic will come from the network, typically from a storage system or from sensors or from some sort of a stream of data. And the FPGA can actually go and start pre-processing this data, pre-filtering this data. Remember this Aqua project from Amazon that I mentioned before, but also can doing things like scatter gather, right? I mean, I can scatter the data across different GPUs. If I have several GPUs, I can actually send part of the data to the CPU, part of the data to the GPU. And when the processing is completed, it can also gather this data from different locations and then send it through the network, do encryption, compression, you name it, right? So we want to have this notion of a smart hub that actually acts as a very, very smart NIC that actually interacts with a collection of heterogeneous components. And we want to do this because today this is done either through the CPU or through specialized components that are not accessible to us. And the idea is to actually build an open source system that allows researchers in other areas that are not a cloud provider to have the ability to tailor this infrastructure to particular application, okay? So now, the other thing that we are doing that I understand that is also of interest to some of you is that we are extending this Slash project, right, with the ability to communicate from the FPGA directly to the GPU. This is something that, for instance, with NVIDIA GPUs, you can do it through NVDirect. But in general, we're trying to sort of come up with a more generic system that is not that vendor specific. We have actually a paper a few years ago where we did this with an AMD FPGA, an Alveo card, and an NVIDIA GPU. We have another prototype open source that actually connects an AMD FPGA with an AMD GPU. And this is something that we are going to continue developing. But of course, this is an area where a lot of specialization is happening through CXL, through things like NVLink. AMD has Infinity Fabric. So there is a slew of interconnects that are appearing that eventually we are going to exploit and try to incorporate into the system. But in terms of what you can do with this, well, now we're in a position to actually move data directly to the GPU, directly from storage, or if it is a stream that is coming from some sort of sensor or data acquisition system, we can actually pump it directly into the GPU. And whenever the results are ready, we can actually take them directly from the memory of GPU, don't go through the CPU, And then that way we actually gain significantly in terms of latency. But whenever you're thinking in terms of future interconnects like PCI 6, PCI 7, or eventually using things like NVLink or Infinity Fabric, we might actually get a far higher bandwidth, which actually starts making a very interesting construction where, as I told you before, the CPU almost disappears, right? We can actually do most of the processing that we need to do without involving the CPU. This can be done directly by allowing the GPUs communicating with each other through the FPGA. For instance, what I told you before, we have this collective communication library implemented on the FPGA, and now this is accessible to the GPUs that can actually use this collective communication library to actually contact all the GPUs in a cluster, in a rack, right? And actually exchange data in a very easy way, right? I mean, and it's actually not only efficient, but also simplifies the development for people who are actually building these systems, okay? So let me just conclude with a couple of use cases, and then I hope that we have enough time for questions, right? So one first use case, and I'll give you one that we work together with SAP, so just to sort of to see or to demonstrate that what we are doing is relevant to somebody who actually processes a lot of data. SAP has a database, in-memory database called HANA, and this database actually has quite a bit of traffic going to disk, right? I mean, whenever you load the data, whenever you actually have to do checkpoints and things like this. Just to cut a long story short, what happens is that this data needs to be encrypted and need to be compressed. This is an expensive operation because you use a CPU. That CPU is not available for running queries. That means that every time you actually have to write this data in or have to write this data out, you're losing performance that is not available for processing queries. So what we actually did is we actually, using an FPGA, we put a smart NIC that actually you give it the data, and it will actually, on the way out, it will do compression and encryption. So your data will go to storage, compressed and encrypted, and on the way in, will decrypt the data. We are not doing decompression because for the type of decompression algorithm that they use, the FPGA is not quite adequate, but at least we have done the decryption, and this is moved to the CPU, where you do the decompression and the data can be actually processed there, right? And what you see on that graph is that on the lines, the green line and the dotted line, this is the performance that you get from the CPU. We are comparing with 1 or 2 threads because you might actually complain about this and say, okay, no, but a machine has maybe potentially 80 threads. Why are you comparing with 1 or 2? Because in a database, you don't devote the whole machine to I/O. There is only 1 or 2 threads on the CPU that are devoted to I/O because the other cores, the other threads, are actually busy in running queries, right? So that means that we actually have limited resources. And we saw that by actually doing this on an FPGA that can be embedded on the data path, on the I/O path, right? I mean, you actually get a significant boost in terms of performance, right? I mean, so this is something that we did together with people from SAP. And in fact, this work received an award, right? I mean, from in an industrial track of a conference, right? I mean, because it's something that a lot of people are very concerned about, this overhead of the I/O. Something maybe a little bit more relevant for those of you interested in AI. This is another example of something that we have done with these accelerators and all this infrastructure that we have been building. This is an example taken, this is a use case taken from Alibaba. A few years ago, they came to us and they say, well, we have this recommendation system. These recommendation systems, what happened is that you have input that you receive, and then you want to do inference over this input, right? And what happens is that you have dense features, and the dense features go straight into the neural network, right? I mean, so that is not to the bottom part of recommendation system. However, there are features that are actually sparse. And these sparse features, before you can actually process them, you actually need to go through an embedding table, right? I mean, so the embedding table, you have to go through an embedding table. And this embedding table ends up being a major performance bottleneck. Why? Because these embedding tables involve a lot of random memory access. And this on a GPU does not really work well. So for them, this was a major problem because it was limiting the latency that they could actually get. It was limiting the throughput. It was actually forcing them to use more hardware, right? I mean, not being very efficient, right? And then they wanted to come up with a different way of doing this. So we look at this problem, and the interesting thing is that when you profile the models that they were using, you see that the embedding lookup, right? I mean, this is for small models, medium models, and large model. the lookups are between 80% and 60%, 55% of the time of the computation. So actually, the computation of the recommendation model was much smaller in terms of time and the resources needed, right? Actually, embedding lookup. So embedding lookup was really the bottleneck. So what we did is we actually, if you're interested, I can tell you later, or you can actually go and look up the paper and then ask me questions, right? I mean, if you're interested, what we did is we actually implemented the lookups on an FPGA that we put on the data path, right? And then we combine this with a GPU. And what we can do, thanks to all this infrastructure, the fact that we have networking, the fact that we have the ability to communicate the FPGA with the GPU and all those sort of things, is that we have a very flexible system that allows you to take a set of FPGAs, a set of GPUs, and then you can actually, as the figure shows, you can actually have one particular model that uses one FPGA and one GPU. You can actually have, for very small models, you can actually have everything on an FPGA, but you can also have models that share one FPGA, and one of them uses 2 GPUs and the other one uses 1 GPU, because we can actually send the traffic for different requests to different places. Or you can actually have a model that requires FPGAs, requires a CPU, because the embeddings do not fit on the FPGA memory, and then you use a GPU for running the recommendation system and so forth. So we can actually come up with arbitrary configurations and combinations of heterogeneous hardware in a very easy manner, right? I mean, and all of them with a significant performance improvement, right? So this is actually quite interesting. At the time we did this, we did it with interconnection through the network. Today we are trying to do this with through the interconnect, as I said, with this direct connection FPGA GPU, where we are going to gain significantly in terms of the bandwidth available, right? Okay. And the last thing that I want to mention, I already mentioned it, but just to sort of show how we're actually evolving these things one after each other, right? The other thing that we have is this collective communication library, this ACOL Plus, and this is a paper that we published last summer at OSDI, right? And what this actually allows you to do is to actually communicate across FPGAs, and using scatter gather, broadcast, all those sort of primitives that we know from MPI, right? I mean, from high performance computing, and allows you to do it in a very simple way. We have this implemented on top of TCP/IP. We also have it implemented on top of RDMA, and eventually we want this to have this combined with the direct connection to the GPU, so that the GPU can actually call these collective libraries, right, directly. Okay, so with that, I finish, and I will be very happy to take any questions, right? I mean, or challenges, or hear your comments about some of these ideas and all this work, right? We are in an era where hardware acceleration and specialization are definitely here to stay. To an extent that often, because it happens, a lot of these things happen internally to the cloud providers, we are not really aware, right? We have a lot of bottlenecks and inefficiencies in data movement, and in order to deal with those inefficiencies, we need to come up with different architectures than what we have today. We need to sort of do much more processing along the data path. We need to do much more processing close to the data. This is something that at CERN, with your sensors and the volumes of data that you have, you're very familiar with it, but this is not true in many other applications, right? And we actually need to improve it much more, right? And we need to actually use one technology, the fact that it's a specialization is happening, to solve some of the inefficiencies that we have in terms of data processing, right? By moving processing into the network, by actually having reconfigurable implementations on the FPGA that allows us to change algorithms and evolve them with time, right? And enable new architectures, okay? So with that, I finish. Thank you very much for your attention, and I'm very happy to answer questions, right? I mean, I think we have a few minutes until the end of the slot. Correct, Stefan?
Yes, we have more time. Thank you very much. Excellent talk. Thank you very much. Are there any questions to Gustavo?
Or comments? You don't need to have
comments.
Comments. Yes. How much of these overlaps with the type of things that you're doing, right? I mean, in high energy physics, right? I mean, or for some the particular work that you're doing, right? Both whether you're working on a data center or you're working close to the sensor, right?
First one, Anna, please go ahead.
Hello, I will break the ice. Thank you very much for this great talk, Gustavo. I was actually curious about this GPU FPGA project you presented on slide 20.
Yes.
And I was wondering, actually, what is the latency and throughput you achieve in this system that you have presented there?
So off the top of my head, I cannot tell you what we get because this depends on the combination of GPU and FPGA and interconnect. So we are the latency that we have is in the order of microseconds on the original work that we did with an Alveo card and an NVIDIA card because we were using NVLink. And that is relatively efficient. We have other systems that use maybe versions of PCI that are not as efficient and that actually we lose a bit of latency there. Of course, we are doing this for future interconnects. So the idea is that we want to have this ready for whenever PCI 5, PCI 6, PCI 7 appear, eventually CXL, but also try to combine this eventually with things like NVLink and Infinity Fabric and all those things that potentially are going to give us much more bandwidth and much more latency. But that is something that eventually we need to sort of improve, right?
Okay, microsecond is interesting. Thanks.
So the microseconds come because the FPGA can work a line rate. We can do RDMA. We know that the RDMA to the FPGA is in the order of microseconds. And then at the speed that you can actually move data from the FPGA to the GPU, it depends how they are connected. If you are going through PCI, you can probably do microseconds, right? I mean, also, of course, depends on how much data you're moving. But it should actually be microseconds. But whether it is 10 microseconds or 200 or 300 microseconds, this will depend a little bit of what type of connection and what version of PCI you have and so forth.
Okay, thanks very much. So this has to pass via PCI Express. It doesn't. It's not a direct connection between the GPU and the FPGA.
It depends how you connect them, right? I mean, so potentially, yes, we could actually do a direct connection. In the case of, for the type of things that you do in CERN, right? I mean, a direct connection might actually be the way to go. In a data center, people don't like to have direct connections because this involves particular cabling between the FPGA and the GPU, right? I mean, which is more complicated. And you need to have the particular chassis for actually doing these things and so forth, right? I mean, so this is why in the future, the expectation is that you will use whatever interconnect is in there, right? And if you are on the CXL world, this will be PCI. If you are in the NVIDIA world, it will be NVLink. And if you are in the AMD world, right, it will be Infinity Fabric. But this is all evolving very quickly, right? So I cannot tell you which one is going to win and what is going to happen in the future. Right?
Okay, thanks very much.
Charles.
Hi, yes, thanks for an incredibly interesting talk. So I was curious if you could say a little bit more about offloading compression tasks to FPGAs. Kind of curious as to what kind of benefits you see there, and also what kind of technologies, compression technologies would be supported. Because I'm thinking that even if you can certainly speed up the compression task itself on the FPGA or whatever other hardware, you still have to move the data back and forth. And that still takes a lot of resources, and compression is very data intensive. So can you say anything more about that?
Right. So it's an excellent question, right? And this is actually something that requires a bit of a longer answer. So allow me to actually answer it. So whenever you're talking about the cloud, a lot of these accelerators, of course, if you can actually get a performance improvement, that is fantastic. But it is not always about the performance improvement. Very often it's about freeing up resources on the CPU, right? So if you can do it at the same speed that you do it on the CPU, but you don't use the CPU, then you already have a gain because you're freeing up the CPU for something else, right? Or maybe you actually are freeing up quite a few cores, right, by using just a single FPGA. Now, the trick in many of these things is that you are doing this on the data path. The data already has to go out. For instance, encryption, whenever you do it on the cloud, or what we did together with SAP, sorry, encryption, compression, right? Whenever the data has to go out, it is already going out from memory, has to go through PCI, has to go to the NIC, and then goes to storage. And the only thing that you're doing is you're putting an FPGA on the data path that actually does the compression, right, as the data flows. You're doing this a line rate, a PCI line rate, right? I mean, a network line rate. So you are not adding latency, and you are freeing up the CPU. What algorithm you use? Well, there are algorithms that actually are more amenable to supporting hardware than others. This is why Microsoft came up with this zipline algorithm and then the Corsica implementation. We have done this work for other compression algorithms, right? I mean, on FPGA. But in general, it is not necessarily that the FPGA is going to be much faster. Is that the data is going to move anyway, because you want to write this data out, right? And you're actually freeing up the CPU. And of course, the FPGA typically for many of these tasks is actually much faster than the CPU. Right? Does that answer your question?
Yes, thank you. That was exactly what I was looking for.
Right. Thanks. Yeah, Maximilian.
Hello. Can you hear me, first of all?
Yes, I can hear you. Perfect.
Okay, great. Thank you very much for this very interesting talk. I have a more generic question. And given that you work on a lot of projects, for example, the ones you explained in this presentation, I'm aware that the answer to it may differ depending on the specific project, but yeah, I will ask it anyway. So when you develop these systems, what methodology or what tools do you use for determining any remaining bottlenecks to solve? So exactly what do you do to profile these systems?
So typically for the ones we have use cases, right? I mean, we actually go and run the system, and then we instrument the system as much as we can, right? I mean, if we have access to the code, and then we try to figure out what is the bottleneck. Are we facing a memory bottleneck? Is it a computation bottleneck? Is it a PCI bottleneck? Is it a network bottleneck, and so forth, right? Or is the I/O, and so forth. And then we try to figure out exactly where things are going to happen. In some cases, like for instance, in the use case that I mentioned from Alibaba themselves, they already told us the problem is the embedding lookup, right? I mean, so just go and check how much you can actually gain. And this is where we actually did this, right? In other cases, it's a question of measuring what is happening on the network, right? I mean, so if we can actually put so much data through the network, right? Let's say 10 gigabytes per second, and you see that the final rate of processing, right, is only 2 gigabytes per second. So somewhere you're losing 8 gigabytes per second performance, right? I mean, and the question is that where are you losing this? Is because of the data transfer through PCI? Is because of the CPU? Is because you are going through memory to the CPU? And again, you can try to instrument, you can try to accelerate, you can actually change the architecture a little bit and see where things go, right? So we use a wide variety of tools, right? I mean, typically a lot of instrumentation, a lot of the tools with FPGAs and GPUs, right? I mean, come with performance analysis tools that we use, also the CPUs, and that's typically what we use. Is that what you were asking?
Yes, thank you very much.
All right, great, thanks.
Maybe I have one more question.
Yeah.
Is my bread and butter job is GPU programming for Monte Carlo event generation, which is the simulation application in high energy physics. We are heavily depending on double precision floating point calculations, or even higher precision, quad precision if we go to more complex processes. Or the GPU market, unfortunately, is going in completely different direction. If we, at best, if I understand correctly, with Blackwell, with the next GPU brand, the floating point flops on double precision stay constant at best. So you have any suggestion on how to, in a specialized environment, how to go about this?
You have a problem.
Thank you.
As you said, things are going exactly the other way, right? I mean, LLMs and AIs and things like this, it's all about reducing the latency and reducing the cost of data movement, and this is why it's heavily quantized, right? I mean, people are doing integer arithmetic. The TPU is integer arithmetic. It's not floating point. And I cannot imagine that there is enough demand for GPU vendors or any of these specialized devices, right? I mean, to actually put more effort on increasing the performance of floating point operations.
Okay.
At a certain point, of course, I very much suspect that you don't have enough volume, right? I mean, to justify coming up with your own specialized TPU that has floating point arithmetic, right? I mean, one of the things that you can try to do is actually try to sort of see if through prototyping on an FPGA you can come up with something that is economic enough to build some form of ASIC that will actually do this, right? But I don't think that the trends right now are in your favor, unfortunately.
Thank you. Okay, thanks. Any more questions? Quentin, please go ahead.
Yes, hello, can you hear me?
Yes.
Yes, thank. So first, yes, as the other, thanks for the really interesting talk and inspiring talk. I have a very practical question. Say that we currently have some acceleration algorithm implemented in FPGA using the AMD X30 shell, and we would like to experiment and play with RDMA. What would be your advice to get started in this direction?
Well, write me an email.
Okay.
So we're about to release the next version of the RDMA. It actually works with you can actually make it run on XRT, right? I mean, but also on our own shell. So in principle, the question is that what parts of RDMA you actually need at what level, right? I mean, because you can operate at relatively low level and then you can just need the core of RDMA, or you need additional support, and then we need to sort of figure out exactly how to do it. However, what we can run on Coyote is the same thing that you can run on XRT, right? I mean, so the Coyote shells, so the virtual FPGAs that we have in there will take anything that runs on XRT, will also run inside of Coyote, right? I mean, so if you're interested in this, contact me, right? I mean, and I can actually put you in touch with the team here at ETH, but also the team at AMD, right? I mean, who is developing this. And then we are happy to sort of look at your case and see how we can actually support it, right?
Okay, yeah, that would be great. Thanks.
Sure. All right.
Okay, any more questions to Gustavo? I don't see any.
All right. So if that's not the case, then really thanks a lot, everybody, for your attention, the questions. I hope that it was interesting. And if you want to know more about these things, please do not hesitate to contact me, right? I mean, you know where I am. And happy to learn about more use cases or more potential uses for this technology.
Okay, thank you very much. Thank you very much for the inspiring talk.
All
Perfect.
right. Okay,
Thanks.
great. Bye
Have a
bye,
nice evening.
everybody. Take care.
Bye bye.
Thanks, bye.